Hello everyone, we will be proceeding with the module 2. This is on the fundamental integration formulas concerning logarithmic and exponential functions. Here you needed to review your differentiation formulas for logarithmic and exponential functions as the integration formulas have been derived from here. Pay attention specifically to the algebraic signs of the derivative so that you will not be confused with the signs later on. This module contains the next set of integration formulas that you may use to integrate a given function. You need to further study the properties of the integrand so that you can decide which among the formulas you know now is appropriate to be used. Hence, you will find the term evaluate the integral in some exercises, or can you do this in some exercises, which I believe you can. The first one will be the logarithmic functions. The natural logarithm function is the function that is defined by the ln of x is equal to the integral from 1 to x of dt over t, where x must be greater than 0. This is so because from differential calculus, we know that the differential of ln t is equal to dt over t. The domain of the natural logarithm function is the set of all positive numbers. We read the ln of x as the natural logarithm of x. Hence, u now is a differentiable function of x. Then we could say that the integral of du over u is equal to ln u plus c. And this will be the main formula for logarithm functions involving the natural logarithm ln. Always take note that the logarithmic formula for integration is applicable when the denominator is a function raised to the power of 1 and the numerator is the differential of that function found in the denominator. Also, the absolute value sign is used for u since the logarithm function does not exist for negative values. Therefore, we can combine this principle with the general power formula. For the general power formula, the condition is that our n, which is part of the exponent, must not be equal to negative 1 because we cannot apply the power formula because it makes the denominator 0 if n is negative 1. So if n becomes negative 1, it is more applicable to use the logarithm formula for integration. Let us have some examples. Let us consider the problem the integral of x squared plus 2 all over x plus 1 times dx. Again, for all fractions, we have to check first if the fraction or the rational fraction that is found in the integrand must be a proper fraction. In this case, the degree of the numerator is greater than the degree of the denominator. This is an improper fraction. So what do we need to do first? We need to divide the numerator by the denominator using long division from algebra. So if we will be doing it, we will be obtaining x squared plus 2 all over x plus 1 is equal to x minus 1 plus 3 all over x plus 1. Therefore, if we incorporate this into the integrand, this is what we get. And if we apply the properties of integrals, we could distribute our integral sign and the differential x with each of the terms that will be found into the integrand, making it the integral of x dx minus the integral of dx plus 3 times the integral of dx all over x plus 1. If you notice the third term is 3 times the integral of dx all over x plus 1. It is in the form of du over u. Why? If we consider the entire denominator, which is x plus 1, and then if we take its differential, it will be equivalent to simply du is equivalent to dx. And this should be found at the numerator. Why? Because if we take, again, I repeat, if we take the differential of the denominator, which is x plus 1, it will be dx plus 0 because the differential of 1 is 0. So we will correct this into the integrand. That is why we place 3 before the integral sign because 3 is a constant and then it is a property of the integral. Since the numerator is complete and does not need any correcting factor anymore, we now can integrate the expression one at a time. Now we get the integral of x squared plus 2 all over x plus 1 dx becomes simply the integral of x dx minus the integral of dx plus 3 times the integral of dx all over x plus 1. Integrating further, we take now our final answer. For the first term, we apply the general power formula, which is x squared all over 2. And then the second is just a property of integral that becomes minus x. And the third term, which we applied the logarithmic formula, and we now believe it is complete because we had corrected already its form into du over du. So it becomes plus 3 ln of x plus 1 plus c. Another example is the integral of 3x squared dx all over 5x cubed minus 1. If you notice, this is already a proper fraction. If it is a proper fraction, there is no need for us to divide the numerator by the denominator. We now can proceed and correct the integrand or the numerator found in the integrand. If we let our u be equivalent to the entire denominator, which is 5x cubed minus 1, taking its differential, we take actually 15x squared dx. And this 15x squared dx must be found in the numerator. If we observe the numerator of this problem, we have a 3x squared dx. But what we needed is a 15x squared dx. So in other words, as if it lacks 15 at the numerator of the rational fraction of the integrand. So if we proceed, the integral of 3x squared dx all over 5x cubed minus 1, we could write it in a way that we could introduce 3 before the integral sign because it is a property of integral. So it becomes 3 times the integral of x squared dx. We divide that by 5x cubed minus 1. Since we had determined the differential of the denominator to be 15x squared dx, we have to introduce 15 into the numerator. So it becomes 15x squared dx as a numerator. But to do that, so that we will not change the value of the whole integrand, we have to introduce a correcting factor before the integral sign, which is the reciprocal of 15. So that will be 1 over 15. But of course, do not forget to still write 3 or consider 3, which we had placed it before the integral sign. So now we can integrate 15x squared dx all over 5x cubed minus 1 because we already have corrected its form into the form du over du. So that we now can take the answer, which is 1 over 5. 1 over 5 came from 3 over 15. So that will be 1 over 5 times the ln of 5x cubed minus 1 plus the arbitrary constant c. Let us consider this problem. The integral of sine 3t dt divided by cosine of 3t minus 1. If we let the entire denominator to be u, which is cosine 3t minus 1, and if we take its differential, that will be actually negative 3 sine of 3t dt. So the condition is all of these terms must be found in the numerator. If you notice, the numerator of the integrand, we only have a sine 3t dt. So as if it lacks negative 3. So what shall we do? We will be introducing negative 3 into the integrand in the numerator so that it will become negative 3 sine 3t dt. But the condition is, if we have introduced negative 3 into the numerator, we have to place the correcting factor, which is the reciprocal of negative 3, and that is negative 1/3. So from here, we already corrected the form of our integrand wherein the numerator and the denominator is in the form du over u. In other words, the differential of the entire denominator is already exactly found in the numerator. So we now can proceed and apply the logarithm formula. So that will be negative 1/3 times the ln of the cosine of 3t minus 1 plus the constant of integration c. There are actually other trigonometric functions wherein they could be in the form of du over u. If they are in the form of du over u, we actually can apply the logarithmic integration. Let us consider the integral of the tangent of u du. Applying our trigonometric identities, we could write this as the integral of sine u over cosine u times du. If we take the differential of the denominator, which is cosine u, the differential of cosine u is negative sine u du. So we will correct the numerator in the integrand by introducing negative 1 or simply the negative sign. Of course, the reciprocal of negative 1 is still negative 1 or simply the negative sign must be placed before the integral sign. Doing this, we made our numerator complete. So we could just simply take now the answer as the negative ln of cosine u plus c. Or we could write this as the ln of secant u plus c. Why? If we apply the properties of logarithms, negative ln of cosine u plus c with trigonometric identities, we could write this as the negative ln of 1 all over secant u plus c. Applying the properties of logarithms further, we can write this as the negative of the quantity ln 1 minus ln of secant u plus c. If we distribute the negative sign, we take negative ln 1 plus ln of secant u plus c. And we know that the ln of 1 is 0, so our answer became the ln of secant u plus c. So, negative ln of cosine u plus c is equivalent to the ln of secant u plus c. So, let us consider an application of the integral of tangent u du. For this case, the integral of tangent 3x dx, if we notice the angle which is 3x, the differential is 3 dx. So we have to introduce 3 into the integrand, and then its correcting factor is 1/3 before the integral sign. So therefore, we could directly integrate this problem. So that will be simply negative 1/3 times the ln of cosine 3x plus 3. Or we could write this as 1/3 times the ln of secant 3x plus c. If we consider the integral of cotangent u du, and if we apply the trigonometric identity formula, we could write this as the integral of cosine u all over sine u times du. If we take the differential of the entire denominator, which is sine u, its differential is actually cosine u du. And we found it that it is already corrected in the numerator, which is cosine u du. So we could simply take already its integral. So that will be the ln of sine u plus c. If we will take the integral of secant u du, it is actually equivalent to the ln of secant u plus tangent u plus c. Why is this so? First, we can multiply the integrand with a correcting factor or a fraction that has a value of 1 so that we will not change the value of the integrand. For this case, we can multiply secant u plus tangent u all over secant u plus tangent u. If we further simplify this, or if we expand the numerator, we take here the integral of secant squared u plus secant u times tangent u. We multiply that by du, and the denominator already becomes secant u plus tangent u. If we take the differential of the entire denominator, taking the differential of tangent u, that is actually secant squared u, which is found in the numerator, and if we take the differential of the second term of the denominator, which is secant u, the differential of secant u is secant u tangent u. So, secant squared u plus secant u tangent u is found in the numerator. It is exactly the differential of the entire denominator. So now, we could just simply apply the logarithm formula. So it becomes the ln of tangent u plus secant u plus c. Or we could just simply write this already following what was given, that the integral of secant u du is equivalent to the ln of secant u plus tangent u. If we will consider another problem, which is negative 5 secant 2z dz. So we already had derived the formula for the integral of secant u du. For this case, the angle is actually 2z. If we take the differential of 2z, that is equivalent to 2 dz. So we have to introduce 2 into the numerator of the integrand, but we have to introduce the correcting factor, which is 1/2, and it must be placed before the integral sign. But do not forget the given constant, which is negative 5. So applying the formula directly, we now can get the answer as negative 5 over 2 times the ln of secant 2z plus tangent 2z plus the arbitrary constant c. So I believe you could take also the integral of cosecant u du, which is equivalent to cosecant u minus cotangent u plus c. I believe you can do this. What about exponential functions? The natural exponential function is the inverse of the natural logarithmic function. It is defined by e raised to x is equal to y if and only if x is equal to the ln of y. The real number exponent, wherein if we have a as any positive integer or it is a constant, x is any real number, we could say that a raised to x is equivalent to e raised to x times the ln of a. The number e is the value of the exponential function at 1. So e is actually equivalent to e raised to 1. And this is constant. We all know this. What will be the properties of exponential function, which is actually introduced in algebra and in differential calculus? To take a review, the first property is the ln of e raised to x is equal to x, and e raised to the ln of x is also equivalent to x. The second property is a raised to x is equivalent to e raised to x times the ln of a for every a that must be greater than 0. The third property is that if e is multiplied, if e raised to a is multiplied by e raised to b, it is equivalent to e raised to a plus b. And the last one, if we have e raised to a, we divide it by e raised to b, that is equivalent to e raised to a minus b. Let me introduce the integral of exponential functions. These are the formulas. First, the integral of e raised to u du is equivalent to e raised to u plus c. The second is the integral of a raised to u times du is equivalent to a raised to u all over the ln of a plus c. So let us review. For the first formula, the e is the base of the natural logarithm, and our variable of integration is u, wherein the exponent u is in terms of the variable of integration. For the second property, the a there is the base where a is any constant. Our exponent is u in terms of the variable of integration u that made it equivalent to a raised to u all over ln of a plus c. To illustrate that, let us have some examples. Let us say we have the integral of e raised to negative 2 minus 5x times dx. Notice that the base here is e and our numerator is in terms of the variable of integration x. If we let u be equivalent to 2 minus 5x, and then if we take its differential, du is equivalent to simply negative 5 dx. So it means we have to introduce negative 5 into the integrand, but we have to introduce also the correcting factor, which is the reciprocal of negative 5, and that is negative 1 over 5. So since we had corrected the integrand by introducing negative 5, then we could proceed applying the formula that the integral of e raised to u du is equivalent to e raised to u plus c. So therefore, we now can write this. Do not forget the introduced correcting factor. That is negative 1 over 5 times e raised to 2 minus 5x plus c. Let's have a second example. The integral of 1 plus e raised to 2x all over e raised to x times dx. If you notice here, the integrand is an improper fraction. Why? Because the degree of the numerator is 2x and then the degree of the denominator is x. We could see that the degree of the numerator is greater than the degree of the denominator. Hence, we need to divide the numerator by the denominator first. When dividing a polynomial by a monomial, we divide each term of the polynomial in the numerator by the monomial in the denominator as introduced in algebra. So what happens if we divide 1 plus e raised to 2x divided by e raised to x? We get 1 over e raised to x plus e raised to x, which becomes the new integrand of our problem. We can write 1 all over e raised to x as e raised to negative x, making now our whole integral expression as the integral of e raised to negative x plus e raised to x dx. We now can integrate each of the terms independently by applying the properties of integrals. For the first term, which is e raised to negative x, the correcting factor is negative 1. So we will be introducing a negative 1 into the integrand before the integral sign. For the second term, which is e raised to x, the correcting factor is positive 1. So there is no need to write positive 1 anymore because the differential of x, which is the numerator, is simply dx. So from here, we now can apply the formula of the integral of e raised to u du, which is actually e raised to u plus c. So our answer will be simply negative e raised to negative x plus e raised to x plus the constant of integration c. Let us have a third example. If you look at this problem as if this is quite confusing, although this is a product of an algebraic term x squared and an exponential term which is e raised to 2x cubed, we have to notice that the algebraic term x squared is just part of the differential of the exponent of e. We can check this by letting our u be equivalent to the exponent of e, which is 2x cubed. If we take its differential, that is actually 6x squared dx, we can see that x squared is part of the differential of u. We only need to introduce a correcting factor of 6 to the differential and 1/6 before the integral sign. So 6 will be introduced into the integrand. The reciprocal of 6 is 1 over 6. That will be our correcting factor placed before the integral sign. So we had corrected already our integrand, so we could just simply apply the formula and our answer will be 1 over 6 e raised to 2x cubed plus the arbitrary constant c. For the fourth example, although this is a product of an exponential term and a trigoterm, we notice that secant squared y is the derivative of tangent of y, which happens to be the exponent of e. Hence, we can use the exponential integration for this. If we let u be equivalent to the tangent of y, the derivative of u is simply secant squared of y, which is exactly found in the integrand. So we could apply the formula directly. So e raised to tangent y plus c will be the final answer. For the fifth example, again, we notice here that x squared is part of the differential of u, and that u is x cubed. If we take its differential, it is x squared dx. So the differential is 3x squared dx. All we have to do is that we will introduce 3 into the integrand and then introduce its reciprocal 1/3 into before the integral sign, and that will be our correcting factor. So applying the formula that the integral of a raised to u du is equivalent to a raised to u divided by ln of a plus c, we now get 1/3 times 10 raised to x cubed all over the ln of 10 plus c. Thanks for listening and watching my presentation. I'll see you in the next presentation.